Audio is still kind of terrible. So we're going to keep moving along though. Now we're into lecture 5, functions. When we talk about functions, let's talk about some relations. A relation is a set of ordered pairs that give a correspondence between values of one quantity and another. Often one quantity is considered an input value and the other one is an output. And relations can come in many different forms. Most common of them are sets of points or tables, equations or graphs. So here we have a set of points, right? This is one example, right? This is a set of points. So it gives us some relation between things x and y. Here's another. It's a graph. This is a circle, right? So all the points along here. It's another set of points, but represented as a graph. Here we have something we're more familiar with, an equation involving x and y itself. This is a relation as well. And so, well, relation is a set of points, so we can list them. What happens when x is 1? Well, we get 1, 0, 0, 1. Right, you can start listing off some points, right? You can write down some of the points to get an idea of what this relation is saying. So, let's get back in the view here. All right, so graphs. Graph of the relation can be in the picture that I haven't drawn yet, but here are a set of points. We plot these points. 1, 1, 2, negative 3, 0, 2. Sorry, 0, negative 2. That's not zoom. Ignore this point. 0, negative 2, 0, negative 2, and negative 2, 1. Right. Ignoring that x because my mind just swapped those numbers out. This is the picture of what this relation looks like, right? Set of points. It's relating x and y. Right. Now, there's another relation, and let's figure out what it looks like. Right? So, from last time, this is a circle, right? Radius 2, centered at 0, 0. So, well, there's our center, right? Yeah, at this point, right, so this circle here are all the points that this thing has, right? So the circle represents that relation. So, domain and range. It's important when we're talking about functions and relations. The domain of relation is a set of all possible inputs, right? So, if we look at this first table here, its domain is going to be a set of it's all the inputs, right? So it's going to be negative 3, negative 2, negative 1, and 0, right? Those are your input values, your x values. And then your range, it's a bad brace, but whatever. Its range is going to be 10, 7, 3, 1, right? All the possible output values. Right. So tables are pretty easy to read domains and ranges off of, which is nice. Now for this graph, actually, shouldn't do that. The domain of this graph is out of bounds. This thing really doesn't want to focus. Sorry about that. Well, I'll just have to write a little bit harder so it can see what I'm writing. Alright. So the domain of this guy is all the possible input values, again, all the x values in this case. So it starts at negative 3. We have a solid out there, so it's included using interval notation. Negative 3 up until x is 0, right? there's an open dot here, so 0 is not included. So it's everything up to and excluding 0. So its range is going to be similar. The lowest point, now we're looking at the y-axis, the lowest point is here at -3. And how high it goes, right, goes up to -1. Open dot is not included, so everything up to not including. Sorry, that was +1. +1. Right? The domain and ranges. Very important and pretty straightforward. So let's take a look at 2 examples of relations. Remember, a relation is it's a set of ordered pairs that give a correspondence between 2 quantities, right? So look at this guy. Your job pays you $15 per hour. You can work up to 30 hours per week. Okay, so T, let's say, is number of hours worked, and P is your money earned. Is there a relation? Yes, sure. It's relating to quantities, right? So if T is equal to 8, right? How much is P? So you get $15 per hour. So it's 8 times 15 is going to give you, what is that, 200 and something? No, that's way. No, sorry. Quick math in the head is not working right now. This is 120. And you should include the units at the end. It's funny, right? You get $120. All right, cool. So this other example. You go to college, graduate, and then get a job. So X is your overall GPA. Y is your annual salary of your job. Is it a relation? Sure. It is relating. It is relating one quantity with another. Size of one quantity with another. If your GPA is 3.52, then Y is. Wouldn't we all like to know that? Because that would predict the future. But we can't answer that because we don't have enough information. Right? Here, we knew what we were dealing with. Here, it's too vague. We don't know what's actually going on. We weren't given any sort of recipe to find out. So this brings us to functions. Function is a special kind of relation. Relation is a function if every input value gives off exactly one output value. So you plug in the value and you get 1 back, exactly 1 back. So it says in this case, i.e. the value produced depends entirely on the input value and nothing else. And that there's no ambiguity of what the output will be once we know what the input is. So for instance, if we go back, this guy is not a function because we can't answer this, right? There's ambiguity. There's that. So, sorry. Let's look at this first one. Is this a function? Oh, look at the input values. There's only one input value of each kind, right? There's only a 1, -3, 1, -2, 1, -1, and they produce different output values. Technically, that's not important right now, but right, all the input values are distinct. So yes, this one is a function. All the values produced depend entirely on one input value and nothing else, right? So each one of these has only one input value, right? Whereas we look at this one, we have 3 and 1 both have like an input value of 5, right? So if we try and plug in 5 to this relation, we either get -3 or that's not it. So we'll look at some other examples and please find that out. in a minute. So for function notation, let's start with that. The function is given a name, often f. You can give it f, g, h, k, j, fred, a whole bunch of different things. Most common one is f. Okay. So with special notation, it relates to inputs and outputs. So this is read f of x. Right? F of your input value equals your output value. So we would say f of 7, in this case, is equal to -3. This is like the same thing as 7, -3, right? So if we were to say, okay, if x is 7, then -3 is your y value, right? If x is 7 and y is -3, this is like some point xy. This is your corresponding function interpretation for that, right? So we have examples here of different functions, right? F of x is equal to x squared plus 4. So you get a quadratic, a line, another line. All of these are functions, right? Because, again, it doesn't break the rule. It doesn't break if every input value produces exactly one output value. Right? This guy wasn't, because it had one input value that produced two different output values, and that's that for function. So how do we use function notation? Let's let g of x equal x squared minus 5. And we're going to determine the following. G of 4. Well, this is the same thing as like if we had y is equal to x squared minus 5. Instead of y, we have g of x. And so if we said if x is equal to 4, then y is equal to what, right? So if x is equal to 4, then we get y is equal to 16 minus 5, which is 11. I'm writing a little small here, sorry. Then y is 11. That's what we're used to, right? That's the same deal over here. G of 4, this is going to be 4 squared minus 5, which is 16 minus 5, which equals 11. So G of 4 equals 11. And so my printer didn't print this in nice color, but you can find it on the other completed notes. A nice little meme for you. All right, so you do the same thing, right? So for every x you see in your function, you plug in its input and see what you get. So this guy is going to be k plus 1 squared minus 5, which you technically can simplify out if you want, but why not? This is perfectly fine right here. But if you want, you can also rewrite it as k squared plus 2k plus, minus 4. Right. Either way works. Depends on what the question is actually asking for. But for using function notation, you are taking the input and plugging it into, so your input is x, you plug it in here for every x you use. If you give k plus 1, give k plus 1 squared plus 5. Smiley face, after the smiley face, I have to make a smiley face, squared minus 5, right? Whatever your input is. Could be red, could be S5, 3, whatever. So, I use function notation. Evaluating versus solving. basically means, are we plugging in for x, or are we solving for your function? So to evaluate a function means to find the output for a given input. So suppose this is our function k of x, and we want to evaluate k of 9. That would mean that we say, okay, k of 9 is equal to 2 times 9 minus 8. 18 minus 8 is 10. So k of 9 is equal to 10. So it's the same thing as like, okay, if x equals blah, and you solve for y, right? But we're using two different words here to distinguish things. And then solve function means to find the inputs that produce a given output, right? So you want to solve k of x is equal to -6. That means k of x here, well, equals -6, equals 2x, that's a minus 8. Okay, and you want to solve for the x value. And this one we had no solving. We were just evaluating. We plugged in the x value and simplified. Let's evaluate. Right, so we solve this and we get 2 is equal to 2x, add the 8 over, and then we get x is equal to 1. Why is this so blurry? Sorry. I still have to try and write a little bit harder. Might use a sharpie in the next lectures. Okay. That's your difference between evaluating and solving. Evaluating from the table. These are nice. These are straightforward, pretty easy, and really fun. In my opinion, fun. So we want to evaluate h of 2. It's the same process, right? So we look at the x of, so evaluate h of 2. All right. So that means x is equal to 2, and we want to find out what the output is, right? So if x is equal to 2, find it on our table, right here. H of 2 is going to be this guy, 4, right? That's our corresponding output. Okay. So now, how about solving? If we solve for h of x is equal to 4, we find out where on our table we are at 4, and that's here and here. Okay. So the x values where h of x is equal to 4, well, just read from the table. X is equal to 8, or x is equal to 2. Yep. There we go. It's straightforward. Tables are nice. Even for your friend. Evaluating from a graph. Same idea. All right, same principle. Evaluate g of 2. Right? So that means we were trying to find out what our quote-unquote y value is. Well, it is. We're trying to find g of x when x is 2. So x is 2 is right over here. So we trace that up all the way on our axis, on our graph, and it's there. So g of 2 is going to be, read off the corresponding y value, and we get 5. Yep. Now how about solving for when g of x is equal to 0? Right? This is our g of x, right? Our y-axis. So trying to find out when g of x is 0, well, that happens all along this line. Where does that happen on our graph? Here and here. That happens at x is equal to -3. Or excuse me, it happens when x is equal to -3 and when x is equal to 1. So it's not. So in this case, it's not asking for points, right? Just want to say, yeah. So in this case, it's asking for you to solve, not asking for the points themselves, right? It's just asking for what x values satisfy this. When is a relation a function? Well, from a table, from a table you want to look for repeated inputs, right? So on this one, -3, -2, -1, 0, all different. So that's fine. That one is good. That's a function. Is a function. Yeah, I'll keep it. I won't write it. The next one, we have 5, 0, 5, 6. Well, we have 5, -3, 5, 1. One input going to two different outputs. That means that it is not a function. From a graph, we can test it via the vertical line test, right? And that means if we draw a line, I'll use blue. If we draw a line anywhere on the graph, and it hits 2 points, then it's not a function. Why? Well, think of it this way. Say that's x. This is y1, or x, y2, x, y1. These are points on the graph. X, y2, or x, y1, x, y2. The same input with different outputs. Right? So that's what the vertical line test is doing. It's doing the exact same thing here up as in the table. So this fails the vertical line test miserably and is not a function. Yeah? This, however, if you try and draw a vertical line anywhere, it will only hit the graph once. So that means that this is a function. Well, this one is a function because it passes the vertical line test. Okay? All right. So what happens if you're given just from a formula? You want to still try and find, are there any inputs that could possibly produce multiple outputs? So if we look at this guy, if x is equal to 9, actually no, let's do 2. Well, 4, there we go. If x equals 4, then we have 4 is equal to y squared, and then we get y is equal to plus or minus 2 if we take square roots. Right? So the one input of x equals 4 gives us two possible answers. So this guy is not a function. No. What about this guy? What's happening in this function or formula? Well, taking our input x, that's not how you spell input. Taking our input x and multiplying by 3. Then you're subtracting 5. So, also, if you want, you can sketch this out. This is a line, and so obviously a line is going to pass the vertical line test. A non-vertical line. This is a non-vertical line because it has a slope positive 3. Also, if you sketch this out, this is a sideways looking parabola, and you'll be able to test it via the vertical line test as well. But these are all like different ways that you can find out is a function. Something is a function or is not a function. And again, it hinges off of that. If you have the same input going to different outputs, you don't have a function, right? Okay. These are more examples. So if you look at this line segment, well, draw a vertical line anywhere you can, and it passes the vertical line test. That's fine. This guy, well, it's bunched up together, but still, you draw a vertical line, anywhere on here, and it only crosses the graph once. So this guy is also a function. We'll see a lot of these more because, well, we'll see a lot of these much later on in the course, but that's a nice sign graph. All right, what about this guy? This guy is not a function. It fails vertical line test miserably, say at -1. Draw a line, we hit the graph at 2 points. Not a function, right? What about this scatter plot of points? Also not a function. Why? Well, it has one input for -4, -2, 1, 0, problem at 1. You can't see it because this thing's really blurry, but anyway, right here at 1, we have 2 points here and here. 1, 2, 1, -2. Same input, different outputs. Not a function. Right? Okay. And also, if you draw a vertical line, it hits both of those 2 points. Same thing. All right. Domain and range from a graph. Well, let's look at this guy. What's this guy's domain? Well, the domain represents the input values, right? And in this case, the input values are the x values. Right? So the input values in this case start at -1. We'll do this in interval notation, actually. So it starts at -1, but it's not including -1 because that's an open circle. It goes from -1 to 0 because we have another open circle. So we go from -1 all the way to 0. Union. We have another interval from 0 all the way to 2. Right? And we include 2 because this is a solid dot. So we have a bracket. And its range, well, what's the lowest point that we have, right? The range is its corresponding y values. It's f of x values. It's output values. So our range, our lowest point is -2. Solid dot, we include it. And then we keep going up and up and up. We hit a problem at 1, right? Because that is an open dot. So that's 1, union. But we still keep going, right? Because the highest point is at 2. So we have to exclude 1 and then go all the way up to 2. Excluding 2, because again, it's an open dot. Okay. Okay. That's our first one. What about this next guy? It's a parallel. Domain. Are there any breaks in this line? Nope. Not line. It's a parabola. So its domain is all real numbers. It has something of the form ax squared plus bx plus c, right? And its range, well, its lowest point is here. The vertex is at -4. And it keeps shooting up to positive infinity. So that's its range. This guy is a piecewise function. And, well, let's look at this carefully. Let's look at its domain. The farthest it goes is, it starts at -4, right? That's our lowest point. So we have, and it's included as a solid dot. So -4 up until, well, it looks like we have a break here at 2. Okay, there's an open dot down here, but there's a solid dot here. So this is actually going from -4 to -2. Well, it's actually included, right? Because we have a solid dot here. Okay, let's look at the next one. At 1, open dot here, but a solid dot there. So if we look at all the x values, this function is defined for all the x values up until 5. Excluding 5 because this last one is an open dot. Right? So look at one of those at the break. If you look at 1, it's in this interval. H of 1 is going to go up here. Right? It's a solid dot. It's defined. So that's our domain. Our range. This one's a little bit longer. Actually, not really. These are horizontal line segments, right? So we only hit -3, -1, and 3. Those are the only 3 numbers that this function takes, right? There's no x value in here, right? If you say f of, let's see, 3. F of 3 is 3, right? Nowhere in between here. So our range is just going to be -3, the set of, well, values, -3, -1, and 3. That is the range for this last guy. A little bit tricky-ish. We just have to look at the function carefully and look at the graph. All right, domain of the function from the formula. So unless otherwise stated, the domain of the function is implied to be all real numbers where it is where its expression is defined. Right. So it's defined by, well, are there any rule breakers? Right. So this function right here, it is a fraction. Okay, nothing against fractions. We just can't have the 0 on the denominator. So we cannot have, so x squared minus 16 can't equal 0, right? For our domain. Well, let's find out when that happens. Actually, okay, hang on. So our domain is all real numbers such that something can't happen, right? So x squared minus 16 equals 0. That happens when x is equal to plus or minus 4, right? You solve it out. So instead of saying our domain is all such that x minus 16 can equal 0, we can write it nicer and more succinctly as your domain is all things such that x cannot equal plus or minus 4. Right? If you want, you could write it in interval notation, and then that would be long, but why not? Negative infinity up to -4, -4 to 4. These are 4s. It doesn't look like a 4, but they are 4s. Union 4 to infinity. Okay. So that's h of x. Let's look at g of x. G of x is equal to 2x plus 4 on the interval 0 to 10. Domain on this guy. Are there any problems with this function? Right, when I say problems, so like this one with the fraction, you can't have 0 in the denominator. This one is just a line. So no matter what input value you choose, you're going to be defined everywhere. So this is just a line, so its domain is going to be 0 to 10. It's going to be that interval. There are no problems, no rule breakers. Now let's look at f of x. This is a square root. Square roots, we can't have a negative inside the radical. We can have 0, right? That's something that gets confused a lot, and I still don't entirely know why, but we can have 0 inside of a radical, right? So we need to find out when 5x minus 15 is bigger than or equal to 0. Sorry. So if we solve this out, we get 5x is bigger than or equal to 15. X is bigger than or equal to 3. So if domain is all real numbers such that x is bigger than or equal to 3, or we can write that shorter by interval notation, including 3 out to infinity. Okay? So finding the domain of the function just means all real numbers where the expression is defined. And you have to find out where the expression is undefined, so you know what to take out for your domain. Piecewise functions. These are fun. These are cool. So you can graph these out if you'd like, and I actually encourage you to do that if this is confusing. But a function can be defined by different formulas on different parts of its domain. So this function f of x is defined on the interval 0 to 10. Right? It gives us a function, gives us an expression for when x is between 0 and 5, and an expression for when it's between 5 and 10. So f of 1, well, f of 1, that's in this first interval. So we're going to have 1 minus 3 is equal to, what, negative 2? Right? F of 5, it is not in this first interval. That is non-equal to sign here. There is one here, so we use the second expression. So this is 5 squared, and that's 25. Okay. And this last one, f of 11, as just said before, this guy's domain is 0 to 10. So when I'm trying to find f of 11, that doesn't exist. It's not possible to find because 11 is outside of the domain, which is 0 to 10. Right. Yeah. So make sure you know what you're plugging in to your piecewise function, or even just your regular function, is inside the domain of your function. Very important. All right. An example here. Give a formula for a function h of x that has h of 6 is equal to 10. So there are many possible answers. Let me give two real quick. One of them, h of x is equal to 10. It's not quite cheating, but this is just a little quick way out of it. This is the function. I'm just going to draw it out. So this is the constant function, the horizontal line, 10. So if I plug in 6, h of 6 is going to give me 10. If I plug in, my axes are way off, so ignore that. But if I plug in h of negative 3, that's also 10, right? So this is one example. That is a function, right? It passes the horizontal, it passes the vertical line test with flying colors, and is a function that has h of 6 as a point. Right, so it's a function that has this point for exposure. It has 6, 10 as a point. Another one, another possibility is, let's see, h of x is equal to 3x minus 8. Yeah, that should work. Well, if I plug in x is equal to 6, I get 18 minus 8 is 10. Right, that's another possibility. So just be a little creative and know that whatever function you give has to have this as a condition, or it has to have that point as a solution. Okay. So the table of values for a function f of x that has f of 2 is equal to 5 and has a solution to f of x is equal to 3. All right. Well, let's make a table. Sure, why not? So it gives the table, so it has to be a function, right? So for every one input, so one input has to have exactly one output, right? So we want a table of values for a function f of x that has 2, 5 as a solution. Right? So it has to contain 2, 5, right? Or the point 2, comma 5, right? These are really starting to move here. 2, comma 5 is the solution. All right, we got 1. Now it also says that we have to have a solution to f of x equals 3. So that means we have to have 3 as a value for f of x somewhere. This has to be a function, so 2 is knocked out of the water. We can't have that. Right? So let's say 1. Right? So f of x equals 3, the solution now is 1, comma 3. This makes sense. All right, and now we just have to have a function for the rest. So let's say 6, 7, 3, 5. Sure. All right. Let's say 0, 1, 4, 6. Right? All these input values are distinct, different. So this is a function. Has 2, 5 as the solution. Has 2, 5, yeah. It has this point, 2, comma 5, and it has a solution to f of x. Okay. Many different ways you can come up with stuff. There are easier things, harder things, but that's how I do it. All right. Sketch the graph of a function g of x that has 2 x-intercepts and 2 y-intercepts. This is a little bit interesting. Well, this is kind of a trick question because a function can't have 2 y-intercepts. Wait, y-intercepts? Yeah, sorry. A function cannot have 2 x-intercepts. Wait a second. Right. A function can't have 2 y-intercepts. There's a typo / problem on the completed thing. Completed lecture no shell. Because if you do, you don't pass the vertical line test. So let's look at a function. Not a function, sorry. Let's look at a circle. This has 2 x-intercepts, 2 y-intercepts. But it fails. Not a function. It fails the vertical line test miserably. Not a function. If you want to try and have 2 y-intercepts, 1, that's probably like gibberish, but it says intercept. Y-intercept 1, y-intercept 2. If you try and have this for any function, it's not a function. Can't have a function. Not a function. So yeah, this question, you can't give a function with 2 x-intercepts and 2 y-intercepts, both. You can give many functions with 2 x-intercepts. You could have infinite number of x-intercepts, but you can only have 1 y-intercept. Okay? That is the end of this lecture.